Thanks for organizing, Max. I'm going to talk about a little project I did recently called xpublish-tiles, which is motivated by the idea that our users at Earthmover just want their data on a map. They don't really care how, but they want fast time to plot. Hmm. My name is Deepak Cherian. I work as a forward engineer at Earthmover. I trained as an oceanographer, worked most recently at NCAR, and I got pretty deeply involved in open source software, particularly X-Array. And that's kind of led me here, where I was going to show you how I put web tiles on a website. Sadly, we're having some service instabilities today, so I can't actually show you a Slippy map. But the idea is you have data that's sitting in the cloud in Zarr or Icechunk format. Um, you can catalog that with our product called Array Lake, which helps you manage your data lake of Icechunk data sets. On top of that, you can run services through a layer we call Flux. The service I'm going to talk about today in particular is called the OGC tiles, or Open Geospatial Consortium tile service. So this is where if you think of Google Maps and you're scrolling around, the browser sends requests for, hey, I need an image for this little square on the globe, and our service will respond with, here's that square rendered from this data. The challenge with this kind of thing is in Earth system science, we tend to see a lot of grids, right? So the one on the top left is the rectilinear grid, maybe the most common one. This is the little air temperature example from X-ray, but there's other ways of specifying grids. You can use the affine transform, common in geospatial rasterland. Projected grids are common for like kind of limited area modeling of the atmosphere. Curvilinear grids that follow the coast in particular, common in coastal ocean modeling, and there's fancier, more exotic ones like the reduced Gaussian grids on a sphere, and then triangular meshes and maybe even helix grids. But our job here is to take the data, however it's represented, and put it on a map. To do that, we built a project called xpublish-tiles. This plugs into the xpublish ecosystem, which you can think of as a way to stick fast API on top of Xarray. And then you can add plugins to xpublish. The plugin we just built serves the tiles API. The tiles basically conceives of the globe as a giant square, and then as you zoom in, the square gets partitioned into smaller squares, and so on and so forth, right? And so the job of the tiles plugin is given a requested square, send back an image or PNG. This powers our Earthmover tile service under the hood, and it builds on a bunch of open source software. And for this talk, I'm just going to focus on the work that we did on correctness, really, to try and make sure that this worked with every grid that was thrown at us. A core approach to testing we used was property testing. So here's the idea where, given some input, and I need to render a PNG, can I assert properties of that PNG for arbitrary data? Right, so here's an example. If I have a data set that covers the whole globe, I should never see a transparent pixel on a map. So here's is a seam at the 180 of the anti-meridian that happened in a previous version of software we were using. And that's a bug, right? This data set covers the globe. You should never see a transparent seam. And so we express a test using the hypothesis framework that says test over a large variety of grids. This could be your longitudes going from negative 180 to 180, 0 to 360, latitude increasing, decreasing, arbitrary data shapes. It does not matter. If you have global coverage, you should never have a transparent pixel. This gets kind of hard when you start dealing with arbitrary unstructured grids, so those reduced Gaussian grids and the way they're distributed. Here's a little problem. On the right, you see that little seam at 180, right? So there's a little gap there in the data. In the rendering of the data, there is no gap in the real data. The problem is the way the data are distributed, there's no connection between points that are at the 180 boundary to the other side of the globe, to the points at negative 180, right? And so when you render this directly with data shader, you'll get a gap here because it doesn't know that this point connects to another one on the other side of the globe. A little trick we played to fix this was you grab the convex hull or the outline of the grid and you replicate that about negative 180 and 180, right? So this line now at 180 is actually the data at negative 180. It's been brought over and we do the retriangulation and then we can render up to not have transparent seams, right? So this is an example of the kind of work we put in to make sure that we can render data as faithfully as we can, given arbitrary input from the user and very little work on the user's end. Another property test that we run is given the same data on the same grid, you should always render an equivalent image despite how that grid was specified. So if you have a uniformly spaced grid, you could express that as in raster world, the geospatial world, they would use a geotransform and a shape to represent a uniformly spaced grid. This basically defines it as an offset, a spacing, and a size of the grid, right? And that gives you a regularly spaced grid. You could do a rectilinear mesh where you have two 1D coordinates that are orthogonal, or you could do a curvilinear mesh where the two coordinate variables are two-dimensional and orthogonal. It doesn't matter, same data, same grid, same image, right? So this is another example of property test we run. Final one, important for web maps is you like to zoom in and out, and as you zoom in and out, you shouldn't see any artifacts. It should be smooth. Um, and so this property is many tiling systems break the world up into a quadtree. So that's where they conceptualize it as a square, and the square is broken up into smaller squares, each of which then gets broken up into smaller squares. And so if I rendered the whole big tile, and then I rendered tile 3, the subset of the big tile should basically be identical to, the rendering of tile 3 independently. And this is true for any of these, right? And so that's a property we now test is like rendering in as you zoom in and out, you should always see basically a consistent image to make sure that's correct. We did a lot of work to be smart about performance. One was we upstreamed a async data loading feature in Xarray that is now used by an async endpoint. So this is important for web services. Uh, Heavily optimized the most common coordinate transformation case, so going from a lat-long data set to Web Mercator, which is kind of the Google Maps projection. And we do a bunch more. There's a little blog post there. You can see the QR code. Talks about the work that we put in. And all of this stuff is open source and ready to be built on. So that was it. That was our attempt to render arbitrary Zarr data sets into a map. It's all open source. It's xpublish-tiles. Thank you.